Okay, use Euler's method to approximate y of 1 for the initial value problem dy over dx equals 2x with this initial condition given and this step size. So basically, this dE as a family of solutions. We're interested in the solution that goes through 0, 0. And as of right now, though we don't know what that solution is, even though we've kind of seen that before, it's a separable equation, we can deal with that shortly in that manner. We want to approximate what y of 1 would be, so for the solution that goes through 0, 0, what y of 1 would be for that particular solution using Euler's method. So let's organize our thoughts. We know that we're going to use Euler's method. We know that the step size is 0.25. We know that this is an initial value. X is 0, y is 0, so that's x naught, y naught. And we know that we're approximating this guy, y of 1. So they're giving us the x coordinate. I don't know what the y coordinate is. That's what I'm supposed to find using Euler's method. I also know that this guy is my slopes at every given point, and in this case, notice it only depends on x. So it looks like y1 depends on the y naught business. I'm plugging in my y naught and 0.25 for my delta x. And then the slope at that 0.00 only depends on double the x value, which will be 0 anyway. So my y1 is 0. And my x1 I know because from 0 I took a step of 0.25 to the right. So what we might want to keep in mind is that we're starting at 0. Our goal is to get to 1. And if the step size is 0.25, it makes sense that I'm going to be jumping 4 steps to eventually get to 1. So I'm going to iterate this method 4 times. So this time when I used my previous step, x1, y1, this is the new y value I got. So I know my y2 is 0.125, and I know I had gone another 0.25 over, so my x coordinate must be 0.5. We get our y3 using x2 and y2, so my y3 is 0.375, and since I had gone another 0.25 from 0.5, I must now be at 0.75. So this will be my x3, y3, whereas these were my x2 and y2 from before. One more step it looks like I have to take to get to approximating what I need. So I'm using x3 and y3 from before into Euler's method, and it spits out my last y value that I was interested in. And the x coordinate, if I've gone another 0.25, I'm finally at 1. So this is what I was in search of. I was supposed to approximate y of 1 using Euler's method. Now what does all of this mean? I keep doing this over and over until I get to that point, and I do have an approximation for it. What does it really mean? Well, for this particular dE, since we're lucky and we know how to get the actual answer, let's go analyze what this guy over here means. So we're going to do by separation quickly. We've seen this before, and we're going to have y plus some constant x squared plus some other constant, so ultimately we'll say x squared plus some c. So this is the family of curves, but we were only interested in the one that was going through 0, 0 because that was our initial condition. So which specific particular solution am I looking at? Well, if I use my initial condition, it's just your basic y equals x squared parabola. The particular solution that I'm looking at is this, and I know what that graph looks like. It's basically the x squared function. And what I just did in going through Euler's method, let's say that's 1, I said, okay, I do know for this one, because I'm lucky, I know which curve exactly it is. I know that at 1, the y coordinate is 1. I know that because I already know the solution for this one. But for most of the times when we look at Euler's method, it's for dE's for which we can't actually solve exactly and find the solution, so we would need approximations to get there. For this one, I ended up with this approximation, and what happened there was I use these successive x and y values to eventually get there. So I created line segments just below, since this was concave up, just below the curve to get there. Let's go look at what happened. So these are the ordered pairs that I got through Euler's method. This was my initial condition, then I got 1, 2, 3, 4. I had to go 4 steps to get to my approximation. So basically this says you started with 0, 0. Then a quarter of the way, like right about there, you were still at 0. And then halfway through with Euler's method, you had jumped up a little bit to 0.125, somewhere there, let's say. Then at 0.75, you had jumped up a little bit higher at let's say 375. And then when you got to 1, you're actually 3/4 of the way up there, under where you really want it to be. So these line segments, horizontal at first, then like that, then like that, then like that, approximate my curve, even though I didn't know exactly initially to begin with what my curve was and what the y value was at x equals 1, I actually ended up getting an approximation with only a step size of 0.25, just a quarter below where I should have been. Of course, if I increase or if I decrease rather the step size and I look at it by 0.1s and take 10 steps to get there, I will have a much better approximation. Right now I'm about a quarter below where I should be. I lie short of where I should be for my y value at x equals 1. So all Euler's does is it takes little line segments to approximate the curve and tell you what your coordinate might be at that location. Now we don't want to do this by hand because, as you can see, it's tedious. Going through all of this, I wouldn't want you to do it by hand. So there are websites and applets and applications or even calculator programs that help you spit out these y values so you don't have to go do the number crunching yourself. So here's one website you can go to where it gives you the slope field in the back graph nicely, and also the differential equation. Whatever you put in, it'll tell you what Euler's method will spit out as the values. So the one we just did was y prime is equal to 2x. I put that as my differential equation. The y prime you don't have to put in, it's already in there. My initial point for the problem we just did was 0, 0, and our step size was 0.25, and I wanted to end it as 1, so whatever x value you want to end at is fine. Then I say create Euler's table, and if I scroll down, it gives me, notice, all the y values that we sat there and we did by hand, which I don't want you to do. So it kept iterating the method, and in the 5th final step at 1, it was 0.75 for the y value. And very nicely it also shows you the slope field in the background and how the curve for that particular solution through 0, 0 gets approximated. So this is a nice website, a good tool. Also, let's say we want to put x squared, another problem that we did. This one wasn't separable and we could not solve it by hand. X squared plus y squared. Let's keep the same initial condition. Let's do a giant step size at 1 and let's end at 3. That's the problem I think we looked at earlier. So I'm looking at this differential equation right here with an initial condition. I'm interested in the curve that goes through 0, 0. I want a giant step size 1 and end at 3. Let's create Euler's table. Let's go look at what happens. It shows you what we had seen before, the line segments that create that curve on the right side. And then also if you scroll down, it gives you all those y values. So at 3, it's equal to 6. If we want to improve, and let's say we want to do a step size of 0.2, let's see what happens. Create Euler table. Notice the approximation to the curve gets much better because it spits out many more y values. And it gives you all the successive y values that Euler's method will spit out, and notice at how big it gets when you get to x equals 3 with a step size of 0.2. So this is a good website, a resource for, it displays the slope field in the background, and also it gives you the values for Euler's method.